work down here. Do, 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 do. Reference.
Probably right here.
Down region for some check. Eyes back. So what do we want there? We got to use the what? See these, right? So we want x is the variable for m, y is the variable for n. So we want g of x to be 0, right? And we want, you know, so we could write this as like g comma. I mean, I don't know what the best notation is, but maybe g comma h would be okay. You could write this like, oh man, g comma h, I think, with the meaning, of course, that g of x comma y is actually equal to g of x comma h of y. That is an element of what? M plus k. Agreed? So, so then we need to calculate gradients of the objective function and the constraint functions, right? And what do those look like? All right, so we calculate. And at this point, you might think, well, you can't calculate that in any kind of like nice formulaic way. Oh, yes, you can. Check it out. The formula for the gradient of f at the point xy is simply equal to x minus y, y minus x. So that's the very much the analog of what we just did. And again, this is example 10 on page 115 of Edwards. So there's that, right? What's the gradient of G1 equal to? Big G1. I'm going to skip the xy if you don't mind. We've got gradient of little g1 of x, and then zeros because there's no y dependence, right? And then we have gradient, you know, well, we can skip ahead a bit. The gradient of the mth constraint function is going to be nabla gm, little gm of x, and again 0. Then we get gradient of gm plus 1. Now we're into the y part. So we get 0 for the x part, and we get nabla h1 of y. And this goes on. Eventually you get nabla gm plus k, which is 0 comma nabla h sub k of y. And, you know, I guess I should emphasize these are all in R2n. Those are all 2n dimensional vectors. And what do we want to solve? We want to solve the Lagrange multiplier equations, which are what? So we need to solve like gradient of f, right, is equal to, like, the sum I equals 1 to m plus k, right, of lambda I nabla g sub I, right? So let's think about how that works, right? You have, on the one hand, I mean, I think we can actually solve these equations. See how it works? We have x minus y is equal to all of these, right? So just the sum I equals 1 to m of nabla gi, right? But on the other hand, we have y minus x, and I've missed my lambdas, right? Sorry. Y minus x is equal to the sum, let's say j equals 1 to k of lambda m plus j nabla h sub j. That's these ones. But what does that tell you? See, this tells me then that the sum over lambda I nabla gi, I equals 1 to m, has to be equal to minus the sum j equals 1 to k of lambda m plus j nabla hj. What is that saying? So now we're assuming if we put x equals to p and y equals to q for the extremal solutions, if you will, then that means that the line, so like if you can imagine, you know, this is m and this is n, right? And this is the point P and this is the point Q, right? Then this line, right, is P minus Q, right? So this equation says that that line aligns with, like up here, you're looking at like the normals to the G's, and down here you're looking at the normals to the H's. These two equations say that the line segment which connects them, the closest points, it has to be collinear with the gradients defining the surfaces appropriately, like the appropriate linear combination of the gradients. In other words, there exists a normal vector to the surface along which the line segment of closest approach must coincide. And that's what these equations say. They also say that to find the 2 points which are closest, you need to find a linear combination of the gradients defining this surface, which matches the linear combination of gradients from that surface such that they're equal, like this. Which is exactly what I was saying intuitively on the basis of the plane and the ellipsoid. But you see, this is so much more general than that. because it literally could be talking about, finding the closest point between a plane in 10 dimensions and like some sort of 5-dimensional sphere in 10 dimensions, like finding the closest point of approach if there is one. This is when I first saw this example as in Edwards, it increased my respect for this book quite a bit. Like this is just a beautiful, I really do wonder who first did this example, like which, I'd like to know the history of this example because it's really cool. Okay, so next up, we want to talk about local extrema. So we've just got about 5 minutes left maybe. So that's just enough time for me to get into trouble. So let me not write a lot. Let me just kind of tell you where we're going, okay? And I know this will be like next week before we get back to it, right? But that's fine. So in Calculus 3, we learned Lagrange multipliers, right? And that was good for when you're on the edge of something, right? But to analyze where something's large, like a function of two or three variables, has a maximum or minimum inside the set, like in the area bounded by the curve. So the bounded curve, the curve which bounds, we use Lagrange multipliers for perhaps. Or you could like parameterize the curve and plug the parameterization into the function and do calculus 1 on that. That's the other method. But what about, how do you find the points in the middle which are min or max, right? Well, you look for where the gradient's 0. A place where the gradient is 0 or undefined is going to be a place where a function of n variables has what's called a critical point. A critical point could be a max and min. It could be neither as well. And then, so then it becomes interesting because we don't always have a bounded region to analyze, right? Sometimes we're analyzing the function like on the whole of Rn. So global max and min becomes less interesting. We're more interested in, is it a local maximum or a local minimum? So it turns out then that there's where we have the second derivative test. In Calculus 3, you remember, we look at like the Hessian or something. Maybe they called it that, maybe they didn't. But there's a particular weird second derivative thing that we look at. I will show you how we can derive that from the multivariate power series expansion. Like what we're going to see is that if you're at a critical point, the multivariate power series expansion is dominated by the quadratic piece. And if we look at that quadratic piece, it is populated by second partial derivatives. And furthermore, we can write it as a symmetric, a quadratic form with a symmetric matrix. And since it's a symmetric matrix, it falls under the clutches of the real spectral theorem, which means we can orthonormally diagonalize it. And in terms of those normal coordinates, there's a very particularly beautiful formula that comes up. And from that, we can naturally and easily derive the second derivative test in Calculus 3. And then the larger story is that if you're looking at a point for a function of many variables and you want to understand how it behaves locally, you can replace the function with a multivariate power series. And that multivariate power series will give you the best multinomial approximation for the function near the point. So, for example, if all your first derivatives and all your second derivatives and all your third derivatives all vanished, then you could find a good approximation for the function with like fourth derivatives. So the things we did in Calculus 2 for power series approximations of functions, they do generalize to functions of several variables, and that really gives us the machinery we need to properly analyze local maxes and local mins. But to properly appreciate that, there's a little bit more linear algebra which we should cover, which we didn't cover yet, which is the quadratic forms chapter. So I probably should start with quadratic forms next time, just talking about how we diagonalize a quadratic form. That's interesting in its own right because it answers a long-standing question about from pre-calculus where we have ellipses that are like this or like that. But what about when the ellipse is sideways? Like how do you understand equations for that? So by studying the problem of quadratic forms and like how to rotate coordinates, we'll see that we can take any quadratic form and we can rotate it to make the equation for like quadratic form equal to 1 either be an ellipse or hyperbola in standard form with respect to eigencoordinates. So we'll see that the eigenvectors play a big role there. So once we have that settled, then we can go back to the functions of several variables, write down the multivariate power series, and then appreciate that the quadratic term in it is a quadratic form, and hence we can use the linear algebra to diagonalize it. And then the other thing is, that, and I won't prove this, is that you can just make up multivariate power series just by just stupidly. Check this out. So if I want to find the multivariate power series, say for f of x, y, z equals to, e to the x times the cosine of yz, well, you can literally just do and multiply it out. I believe that is the entire multivariate power series for this function centered at 0 to 4th order. Because the stuff higher in this is like 8th order. And I think that's everything because, this goes up to 4th order, multiplies the 1, gets me all that. Past that, it's 5th order. 5th order times this, I'm not caring about. 5th order times that, obviously I don't care about. And, yeah. And from this, once you understand the multivariate Taylor's theorem, I can read off from this all kinds of partial derivatives for you. For example, just on inspection here, I can tell you that like fyy equals to fyyyy equals to fy equals to 0 at 0, 0. How do I know that? There is no y squared or y cubed in any of this. And when you understand the multivariate Taylors, there's a linking of the meaning of the coefficients and the partial derivatives. It's a natural extension to Taylor's theorem. So anyway, we'll talk about that too. But I will not prove that the substitution principle is legit. There is some like hardcore analysis in there in terms of like rearrangement of series and substitution. Those are things I don't know if I've ever entirely proved, and somebody pays me more money maybe. Anyway, have a good trip.